All right. Thank you, Thomas, for the introduction. Welcome, everybody. I'm going to share some tips and tricks about how to run MD efficiently and correctly. So let's just jump straight in. If you've ever tried running MD with AMS especially, you know it is very easy. You just open AMS input, you create a system, you select the molecular dynamics task, you click run, and that's it. MD is running and atoms are moving. However, that's not the entire story, because although doing MD is easy, doing MD correctly is less so, because there are all kinds of questions you can come up with, like how do I set all these 20 different knobs that tune the workings of the MD driver, or are my results from my MD simulation reliable at all? Can I believe what I'm seeing? And also, you can ask yourself, how do I calculate a particular property in an efficient and still accurate manner? So I will go through some of the most important topics in this regard. The MD experts among you might find the introduction a little boring because they already know all of that. But don't worry, there will be some specific tips also at the end and during the presentation. So it's not just a textbook introduction to MD. All right, so let's first focus at the very core of any MD simulation, the integrator, because as you probably know, the entire methods of molecular dynamics is arranged around numerical integration of the equations of motion, which pretty much means you have a second order ordinary differential equation, where some potential gives you forces, and you integrate those to get the velocities and the positions. However, unlike general ODE solvers, like the known Runge-Kutta methods, MD tends to prefer a little special integration methods, because one of the most sought after properties of integrators for MD is time reversibility, which translates to energy conservation, and we want our systems to conserve energy. AMS in particular uses the so-called velocity-Verlet integrator, which is a member of a family of so-called symplectic methods. That's a very weird and technical term, but pretty much it means that the integrator exactly conserves some kind of shadow Hamiltonian, not the real Hamiltonian, the real potential of your system, but something else, something with some error added to it, but that shadow Hamiltonian is conserved exactly, or at least it would be conserved exactly in infinite numerical precision and with perfect forces. The difference between the real Hamiltonian driving your system and this conserved shadow one is proportional in the second order to the time step, and so is also the global error in positions. So the error in positions that accumulates over some particular time interval, not over a single time step, but over many time steps, is also proportional to a square of the time step. What this all means in practice is that setting the time step is fairly important and has some important effects on the stability and accuracy of your MD simulation. So I've just run a simple test with 300 flexible water molecules with a tip 3B potential at room temperature with different time steps, and this plot shows the evolution of the total energy during the simulation. And you can see that the shorter time step, the half femtosecond one, is a very flat curve down here, shown also in the inset. When you bump up the time step to 1 femtosecond, you get a little higher energy. So your shadow Hamiltonian and the real Hamiltonian diverge a little, and the noise increases a lot. Again, also due to the forces not being completely perfect. But you see that there's no obvious drift. The initial energy and the final energy is pretty much the same as far as we can see over these 50 picoseconds. If you go again a factor of 2 higher to 2 femtoseconds, there is a big change suddenly because the energy jumps up by a lot, by like 50 calories per mole, maybe 40. And also the fluctuations, the noise increases many times. So we see something's already happening here. And even though this curve still looks fairly benign, you don't see any long-term drift here, and you could be ready to accept this as a reasonable simulation. It is very much not so, because if you just go a tiny bit higher to 2.5 femtoseconds, the simulation completely crashes. Energy starts growing out of the bones right from the start, and the simulation explodes very soon. So we can see that overdoing it with the time step can have some severe consequences on your simulation. So how do we pick the right time step? One important key point is that the Verlet integrator, by virtue of being a simplicity method, does not produce an energy drift. Some other integrators would give you an energy drift, and energy that's not conserved very well. Here you won't see that. There will be some drift if you simulate for a very long time, like for nanosecond time scales. There will be something that's due to the finite precision of the numerical integration, not due to the method per se. But any drift that you can see in actual real simulations is due to inaccurate forces. So with some potentials, this is very much of a problem. Some potentials have very noisy and very approximate forces, and this translates to a drift in the total energy in simulations. That's, for example, the case of ReXFF, but also some quantum chemistry methods will give you the same thing. Simple non-reactive potentials like this water model I've shown don't really have that issue much. However, symplectic methods become unstable when the time step crosses some threshold, which is 0.225 times the period of the fastest motion in the system. So most systems you will be working with might contain some bonds with hydrogen, like OH bonds, but also NH bonds, CH bonds. They're all pretty much in the same region, and these vibrate with a period of about 10 femtoseconds. So that already tells us what we saw on the previous slide, that when you cross 2.25 femtoseconds, things will suddenly go wrong. But even if you don't have any hydrogens in your system, you can't go much higher with the time step, because the next fastest group of bonds is the kind of bonds like CC bonds, which vibrate somewhere around 16 to 20 femtoseconds, depending on the bond order. However, this is just the bare minimum, the very limit of stability. But to get any kind of reasonable accuracy in your simulation, you should stay under a tenth of this vibration period with your time steps, which pretty much means that there is a good reason why you always see 1 femtosecond time steps used with systems containing hydrogens, and maybe 2 femtoseconds with systems with only heavier atoms. Before we go to the next part, let me review one important term in MD, which is called ergodicity. That's something that stems from the so-called ergodic hypothesis, which tells you that an ensemble average of a particular property is the same as its time average, which pretty much means the same as running a single very, very long simulation will give you the same information as many independent short simulations of the same system. This is because a system that's ergodic behaves in such a way that it's eventually spends equal time in equal volumes of the phase space. The phase space is some space that's described by all the positions and all the momenta of your system. So any point in there is one particular combination of atomic coordinates and atomic velocities. And when a system is ergodic, if you give it enough time, it will visit all the possible states in the phase space. There should be no isolated islands of the phase space that are disconnected from the rest. So there shouldn't be any short periodic trajectories where your system will just keep jumping back and forth between a few closed states and never explore the rest. That shouldn't happen in an ergodic system. And that is one important assumption that we use when we run simulations. We assume that no matter where we start from, we will eventually sample the things we're interested in, so the actual physical behavior of the system. When I'm talking about ensembles, I need to review that there are a few of them. What I have described just a few slides before was the so-called microcanonical ensemble, which is something that is defined by a constant number of atoms, a constant volume, and a constant internal energy. So you can imagine that you have just a flask that's perfectly insulated, so it does not exchange any heat with the surroundings, and also is closed, so it can't exchange mass, it can't exchange any atoms. However, although this microcanonical ensemble is very easy to study theoretically and also reliable to integrate in molecular dynamics and thus also accurate, it is not very realistic, because in the real world, you don't typically see small systems of a few thousand atoms completely isolated from the surroundings, not being able to exchange anything. That's simply not the kind of systems you would see in a laboratory or in the real life. Real-world systems typically exist in some known external temperature and either a given volume or a given external pressure. So this is why people have come to went to a great length to simulate different kind of ensembles in MD. Most importantly, the so-called canonical ensemble, which uses a constant temperature and constant volume. So it is something that can exchange heat with the surroundings, but not mass. And also the so-called isobaric, isothermal, or NPT ensemble, which can also change its volume in response to the external pressure. There is also the so-called grand canonical ensemble, which would correspond to an open system, but our MD driver enhanced does not support that. We do only have GCMC, so grand canonical Monte Carlo, but not grand canonical MD. Okay, so let's look at the methods that you can use to get this canonical ensemble, get the constant temperature into your simulations. Probably the most well-known thermostat is the Berentzen thermostat. That is a simple method that just emulates the effect that a heat bath would have. There's no real heat bath, but the method just rescales the velocities of the atoms to keep the kinetic energy in the right range. The amount of heat transferred in every time step is proportional to this term. So the deviation of the current temperature from the target one divided by this tau parameter, which is just some input parameter that tells the thermostat how strong to be. The advantages of the Berentzen thermostat are that it is perfectly stable, that there's nothing that can break in this formula. It will be always able to cope with systems arbitrarily far from equilibrium. So no matter what happens in your system, no matter how much energy will get liberated by some process, the Berentzen thermostat will be able to drain it away. And it also has a nice property that this formula gives this exponential relaxation. So it fairly quickly approaches the target temperature. There's an exponential decay towards the target temperature. And the time constant of this exponential decay is this tau parameter down here. There's more than a couple of disadvantages with Berentzen thermostat. Most importantly, it does not generate the correct canonical ensemble. The fluctuations you will get with a Berentzen thermostat in your simulation are much, much smaller than they should be. This is because the microcanonical ensemble does have some amount of natural fluctuations, and the canonical, the constant temperature ensemble, should have higher fluctuations than the constant energy ensemble. However, with Berentzen, this is the other way around, and the thermostat ensemble would always have smaller fluctuations than a microcanonical simulation. This is because this exponential relaxation strongly suppresses or damps any fluctuations that the system would try to do. For this reason, it does not generate a correct distribution. It is also fundamentally incompatible with some methods like temperature replica exchange MD. That's simply because the distributions are way too narrow, so you will never get correct exchanges between replicas in REMD. There's also no conserved energy quantity associated with the Berentzen thermostat, so although you could check the quality of your forces and the accuracy of your simulations in microcanonical simulations, you can no longer do that when you use the Berentzen thermostat. There will be no quantity that should be exactly conserved. Also, if you set the time constant too low, you will get all kinds of severe artifacts generated due to the way the thermostat works. The most well-known of them is the so-called flying ice cube effect, which we'll come to a little bit later. The alternative of the Berenson thermostat in AMS is the so-called Nozay-Hoover thermostat. That is an explicit simulation of a real heat bath around your system. So there's an additional degree of freedom around your system, which simulates the energy of the heat bath, and the transfer of energy back and forth is integrated in time, just like the atomic positions. The original idea was devised by Nozay, but it was then reformulated to be more practical in simulations by Hoover. And we use a variant of this thermostat called Nozay-Hoover chains by Martina Klein and Tuckerman, which pretty much means an arrangement like a Russian doll, a set of heat baths nested in each other, which improves the properties of this thermostat. So there will be more than one additional degree of freedom, but you don't need to care about that all that much. The advantages of this thermostat is that it generates the correct canonical ensemble with the right fluctuations and the conserved energy, which you can then check in AMS movie. And it is relatively safe across a range of the time constants, so you don't need to pay too much attention to how you set that value. The simulation should generate the right ensemble unless you get the time constant very wrong. The disadvantages of the Nozay-Hoover thermostat, most importantly, are that it only works well for systems that already start fairly close to the equilibrium. If you have a big disturbance for some reason, because you started from a very wrong initial geometry, for example, the thermostat will act in a very weird way or potentially crash completely. The original Nozay-Hoover thermostat strongly oscillates when disturbed, so you will have a long time when energy will be sloshing back and forth between the heat bath and the system, and this will take a long time to dissipate. This is less of an issue for the Nozay-Hoover chains that we are using, but there's still some kind of that behavior hidden underneath. This thermostat can be potentially non-ergodic if you set the time constant too short. This is a big issue for the original Nozay-Hoover, less important for Nozay-Hoover chains with typical systems. It only manifests in very, very special test systems like a single harmonic oscillator. But there is a danger of something wrong happening if you set tau too short, so be careful and don't go too low with this. This time scale defined by the tau is only approximate. It's no longer a nice exponential decay constant like for the Berenson. It's just some rough indication of what the time scale of these energy exchanges between the heat bath and the system should be. If we look at a little bit of experiments, I've run a simulation of a graphite crystal with Berenson and NHC set to the same time constant, so 500 femtoseconds. And I've done a step in the target temperature, so what went from 300 to 600 kelvins to show you how the thermostat reacts to a change in the heat in the system. And you can see that the Berenson thermostat, which is this purple curve, very quickly relaxes to the target. You can somehow make out the exponential dependency here. You can see that with a time constant of half a picosecond, in a few picoseconds, you're already pretty much there. The NHC thermostat takes longer because its relaxation is mostly linear, but it eventually gets there. It just takes much longer time than the Berenson, maybe a factor of 2 or 3. Looking at the total energy, you can see that with Berenson, there is a complete lack of fluctuations. There's pretty much a flat line all the way to the disturbance, then the exponential relaxation, and then again a flat line. Compared to that, the NHC thermostat, the Nozay-Hoover chain, starts fluctuating even before the disturbance is triggered. So that tells you that yes, these oscillations are natural and not something that would be just triggered by this temperature shock that I introduced. But you can see that after the shock, there's still a lot of oscillations. They will decay a little bit in time, but there will always be some oscillations. So how do we define the time constant for the thermostat? I already mentioned that if you thermostat very aggressively, you may get artifacts. For the Berenson, this is the so-called flying ice cube effect, because the thermostat will eventually pump energy from the high-frequency vibrational modes in the system into the low-frequency vibrations, rotations, and potentially a net translation of the system. So if you just simulate a cluster of water molecules with a Berenson thermostat with a very low tau, you will eventually end up with something that's completely frozen, non-vibrating, and just tumbling in vacuum. For Nosey-Hoover, the most typical artifact is that you can get potential non-ergodicity if you go too low with low tau, so you will never explore some parts of the phase space. And also the integration of the heat bath degree of freedom can break down completely if you go very close to the integration time step with tau. So a reasonable minimum for both thermostats would be on the order of 100 femtoseconds. Never go below that unless you have a very good reason to, because even if you know if you need a very strong thermostat, 100 femtoseconds is about as strong as you can go before introducing severe artifacts. But any kind of strong thermostating can still disturb the natural dynamics of the system. So dynamic quantities like viscosity or diffusivity can be affected by this. So if you run production simulations and you are already close to the equilibrium, use a high enough time constant comparable with the natural relaxation time scale in your system. For liquids, it would be the correlation time, which, for example, for water is on the order of 2 or 3 picoseconds. For solids, this can be very different depending on what particular material you're looking at, but it is typically in the range of like a half a picosecond to a few picoseconds, depending on the phonon lifetimes in your solid. When you have a heterogeneous system, that's one additional issue you need to be aware of. You can get a net temperature gradient in your system if you just thermostat it as a one big system. This is called the hot solvents cold solute problem in biomolecular simulations. It's a typical example when you have a protein embedded in a box of water, and the force errors on the water molecules are higher than the errors on the protein, so there will be more energy flowing into the water than into the protein. But if you have a one shared thermostat, it will be draining energy from both parts at the same rate. So the protein will be subcooled, will be under the target temperature, and the water will be hotter than the target temperature, and you will see a flux of heat going from the solvent into the solute. The solution for this is to use 2 separate thermostats. So you define a region in AMS input, one for the protein or for your solute, one for the solvent, and assign 1 thermostat each. That way there will be no unequal draining of energy. Each part will be thermostated at the right rate. Let's now take a look at barostats quickly. The Berenson barostat is fairly similar to the thermostat of the same name, but instead of scaling velocities according to temperatures, it scales the volume of the system according to pressure. That's pretty much all that there is to say about the Berenson barostat. It still has the same properties as the Berenson thermostat. It relaxes exponentially, does not generate anything like the correct ensemble. The fluctuations are all wrong, and it does not have any conserved energy. In contrast to the thermostat, this time constant here, this tau p, is only valid if the system has a particular bulk modulus, because there's this product of k times type p in the denominator here. In AMS, we default to 2.2 gigapascals, which is the bulk modulus for liquid water. If your system is very different from liquid water, you should either adjust the bulk modulus input parameter on the expert AMS panel in the GUI, or you will have to rescale the tau p accordingly to compensate for this, to actually make the time constant correspond to some time. Just like we had the Nosey-Hoover thermostat among thermostats, there is also a similar method for barostats, where we have, instead of a real bath, a real piston with some weight on top of it, which we can define and which will then apply some kind of external pressure on your system. We use the Martin and Tobias Klein methods, or MTK. This generates, again, the correct ensemble with a conserved energy, just like the thermostat. it can, in contrast to the implementation of the Barons and Barostat in AMS, it can work on any combination of cell dimensions. So you can scale any set of cell dimensions or keep any subset of them scaled by the same factor. We also have a special mode to change the cell shape by keeping the volume constant. If you just know you need a particular density, but you want to have the shape of the cell relaxed. But that's something fairly special. If we look at the barostats in action, so these are, again, this is the water box with 3 different barostat time constants, 2, 5, and 10 picoseconds. And you can see, even though there's not much to see in this plot, you can already see that the magnitude of the fluctuation does not really depend on the time constant. So even this slowest barostat still fluctuates quite a lot, from like 940 to 1,000 something. But the period of the fluctuations depend very much on the time constant. So the fastest one will fluctuate on the order of a few picoseconds, while the slowest one takes maybe 20 picoseconds to get back from one oscillation. If we compare with the Barons and Barostat, we again see there's no fluctuations. Even the slowest MTK is much more oscillatory than a Baronsen with the same time constant. So this makes Baronsen a great method if you actually need to follow this NPT simulation with an NVT simulation. So if you want to take the final geometry and run it with a constant volume, there is a good reason to prefer Baronsen, because that will give you something close to the average density that you can then pick. With MTK, you never know whether you pick the top or the bottom of one particular fluctuation. So getting something like an average density from that would be a little trickier. Like for thermostats, it's important to use a high enough time constant to minimize the disturbance. And it is also recommended to always use a higher time constant for the barostat than for the thermostat you're using, because otherwise the barostat will pick up the task of the thermostat pretty much and will start expanding and compressing your system to cool it or to heat it instead of waiting for the thermostat to do that. When you're starting with a completely new system, it's typically good to first run in constant volume and drain the excess energy from your suboptimal initial geometry. So first just run a thermostat to cool the system down and then turn on a barostat. Otherwise your barostat will expand the system a lot at the beginning to drain the excess energy, and then will take a very long time compressing it back again. So if we would want to see an example protocol for equilibration of a typical system, it could look something like this. This is just an example. Of course, there's a lot of different standard protocols for different kinds of systems, but you would always somehow prepare the starting geometry, either load it from somewhere or generate it in the GUI using the builder or the crystal tools. Then you could think about running a geometry optimization if you suspect that your initial geometry is very suboptimal and will thus generate a whole lot of extra heat at the beginning of your MD simulation and potentially cause all kinds of problems. Then it is typically a good idea to pre-equilibrate somehow close to the target temperature using a constant volume simulation with the Barons and thermostat and a fairly strong coupling to just drain the excess energy off or to heat the system up to the target temperature. This can typically take about 10 picoseconds or sometimes more depending on the system. Then you would follow with a relaxation to near the equilibrium density and constant pressure and temperature with the Barons and thermostats and barostats. The time constants here would be indicative for water. They might be very different for different systems. This typically takes a few tenths of picoseconds. And afterwards, if you want to be running a constant pressure simulation, you could equilibrate using the NHC thermostat and the corresponding MTK barostat until you see the key properties converge, so you get a stable potential and total energy and a stable density. And then you can start measuring whatever property you were interested in. Alternatively, if actually your production run is meant to be in constant volume, it is typically a good idea to equilibrate with the Barons and barostat instead of MTK to reach the average density that you can then pick and use in a constant volume simulation. In connection to this, I should mention that we have two different ways to run a follow-up simulation to something in AMS. There's first something we call an exact restart. There's a restart keyword in the input. On the MD input panels, this is the restart from input option, which I will show you shortly. This is something that guarantees you a seamless continuation of a trajectory that got interrupted, either because you set the number of steps too low or something happened and killed your simulation. But when you restart in this way, you shouldn't change any input settings at all, apart from the requested number of steps and possibly some options related to writing the trajectory. So this is good for recovering from crashes of all kinds, or for extending a given simulation just to more steps. So you run something for 10 picoseconds and it's not converged and you know you need to extend it. This is the typical case where you would use the restart keyword. If you need to do anything else, you can just set up a new simulation and reuse the final geometry and the final velocities. AMS input will offer this to you when you open it on a simulation that's finished. It will offer you to pick up the final velocities and set them up as initial velocities on the MD input panel. This new simulation will be completely independent from the original, so you can change anything in the settings. You can replace Barostat, Thermostat, change anything. There's no link to the original apart from picking up the velocities. If I can show you in practice, when I open this finished simulation in AMS input, wait for it to load. And now I got asked whether to reuse the MD velocities. So if I just select this and click yes, I suddenly get the final geometry prepared here for a new run. And the molecular dynamics input panel has this initial velocities from file, which is pointing to the ams.rkf file from the previous simulation. If I wanted to use the exact restart instead, I would just take this and put it into the restart key here, down here. I can reset this to 0. It doesn't really matter. It's not used when the restart is being applied. And this would be it. So let me get back to these slides. One common complaint about AMS is that the trajectory files are way too big. This is because the trajectory contains most of the quantities that get calculated by default. You have to opt out of writing something if you know you will never need it. This is something we feel is better than not calculating, not writing stuff, and then having to rerun a simulation just because you forgot to write something. So if you have a long simulation and you sample very frequently, your ams.rkf will get fairly big. This can be all customized on the panel called MD trajectory writing in AMS input. You can, for example, disable writing the velocities that will already save about half of this disk space if you don't need the velocities for something like the velocity autocorrelation function. You can also disable writing the atomic charges if you know these are never changing because you have a known polarizable potential or simply because you're not interested in charges. You can also disable writing the bonding tables and the molecule analysis. For example, if you have a non-reactive force field where no reactions will ever happen, you don't need to reanalyze the molecular composition every time step. However, even if you disable writing velocities, using this option, the velocity snapshot that you need for restarting or for continuing another segment of your equilibration protocol will always get written. This is governed by the checkpoint frequency and not by this trajectory writing option. So that was it about how to set up and run molecular dynamics. Let's now take a look at how to use the results and extract the results. For the basic equilibrium properties of a typical condensed phase system, you can typically use AMS movie to plot it for you. So this can be energies, the temperature, the volume, the density, everything is on the MD properties menu in AMS movie. You can also find the statistics on the energies and on the temperature in the text output from a simulation. So if I just open the output from this run here and scroll all the way down to the end of the MD calculation, there's this table with the minimum, maximum, mean, and standard deviation of these basic quantities. So you can check this if you want to know whether your temperature is in the right range and with sort of the correct fluctuations. If you restart, these will be updated, so they will be a summary of both the original run and the continuation. You don't need to aggregate the values manually in any way. All of this is also written on the AMS.rkf file in the MD history section, so you can access this via Python scripting using the KF browser tool or using the dumpkf command line utility to process the data however way you prefer. We also have something for people coming from the old ReaxFF MD program. There's a set of compatibility scripts in this directory, scripting standalone ReaxFF AMS, that can generate the old style text output that ReaxFF would create from any AMS.rkf trajectory. So this is completely general. It's in no way specific for ReaxFF. It's just tailored for people coming from ReaxFF, but you can freely use it for non-reactive calculations or for DFT. One important thing to monitor, especially when you're doing liquids, is the liquid structure. The most typical property you would monitor is the radial distribution function. This is calculated by the analysis tool, or you can have AMS movie plotted for you. It's again in the MD properties menu. The good thing is this does not require long simulations or frequent sampling. A few tens of picoseconds is more than enough to get a reasonable RDF. But the range of the RDF you will see is limited to half the thickness of the box. So always use a decently sized box if you want to see far enough. For example, if I just open this water box here in AMS movie and go to MD properties RDF, I can generate the OO radial distribution function, for example, and have an error estimate calculated by subdividing the trajectory into multiple blocks. Click generate, wait for a short while, and boom, here comes my RDF. And so you can see that this water model is fairly lacking in structure, and that is a known problem of the tip 3P water model. And if you zoom in, you will see that the red line is the average, and the green and blue lines are the standard deviations above and below. So this already tells you how converged your data is and whether you need a longer simulation or not. So let's just close that again and go to the next property, which is diffusivity. This is probably the most commonly calculated dynamical properties, at least for liquids. You can actually calculate it in two different ways in AMS. One is the so-called green Kubo approach, where you integrate the velocity autocorrelation function. The issue with this approach is that it requires very frequent sampling, so you need to have at most tens of femtoseconds between samples, probably much less to get any kind of reasonable accuracy. And you also need many frames to get reasonable statistics, so you will have a very large trajectory before you will be able to extract any usable results. So this approach is not very recommended unless you need a second option to check the second approach against. The second approach is the so-called Stokes-Einstein-Sutherland method, which is a linear fit to the mean squared deviation with respect to time. The advantage of this is that it does not need any kind of frequent sampling. It's more than enough to sample once every 100 femtoseconds or more. And a simulation that's 50 or 100 picoseconds long is typically more than enough for some kind of basic accuracy, like 10% plus or minus. The important part is that the mean square deviation does have a regime in the time below the correlation time, which, as I mentioned before, is about 2 or 3 picoseconds in water, where you have correlated motion instead of diffusion. So you need to discard this when fitting the diffusion coefficients, otherwise you will get nonsensical results. So yeah, you need to have some idea of what the correlation time is and just discard. But you can go very conservative and discard much more, and you will still get a reasonable accuracy. One thing to keep in mind when calculating diffusivity is that it is affected by a very significant box size effect. The diffusion constant that you calculate from a simulation is always underestimated because the periodic boundary images interact with each other. Just to have an idea how important this is for room temperature water in a 20 angstrom box, this is about a 10 to 15% error in the diffusion constant, and it's always negative, so you will always get a smaller value than you should. Fortunately, there is a good correction formula for this, so just remember this or find this paper by Dunweg and Kramer. This is how you calculate the offset that you add to your calculated diffusivity to get a value that you can compare with the experiment. AMS will not do this for you yet, but we might add that at some point. So if we take a look at how this works in practice, let me just open this simulation of this water box. And when we then go to properties MSD, I can just say, yeah, I will be fairly conservative, and I will, or maybe not. Let's just run it with the defaults first. So I generate the defaults, and you can see this blue curve here. That's the calculated diffusion coefficient. And you can see that it is very different at the beginning than at the end, because this is affected by the correlated motion. So you need to discard this entire part of the simulation to get any kind of reasonable accuracy. So you can say, yeah, I'll just discard the first 10 picoseconds, or maybe you could go even further. But yeah, let's just, yeah, then one thing to remember is that this input window always stays below for some reason. So you need to find it and not try to reopen it, otherwise you'll never find it. So let's just start, let's just say we cut off the first 10,000 femtoseconds, and then we'll calculate 400 frames and generate. And now we have something that's much more flat, looks much more converged. And maybe this is already a good guess of the diffusivity of our material, of our water. It's 5.17. Times to the 10 to the minus 9th. Yeah, this is pretty much the published value for tip 3B. So yeah, always look that this is reasonably flat, and that you cut off this first part here. Oh yeah, let me just close this again. One more dynamical property that people are interested in is the viscosity. Compared to diffusivity, it's much more demanding. So if you need a decent amount of accuracy for viscosity, be prepared for a very long and very demanding simulation. The only approach we have currently is the Green-Kubo approach. This time, it's an integral of the autocorrelation function of the off-diagonal components of the pressure tensor. This means that in the ACF menu, you need to set the vector elements to 4, 5, or 6. That correspond to these of diagonal components. It's in the Voigt order, so the first is the PYZ. However, the autocorrelation function is typically very noisy, so you need a simulation that's at least a nanosecond long, typically even more, for any kind of reliable results. Most of the information is unfortunately at the very short timescales in tens of femtoseconds, so you will have to sample much more frequently than every 10 femtoseconds to get any kind of reasonable accuracy. So be prepared for a very large trajectory when you calculate it this way. The autocorrelation function will eventually drop to 0 at around the correlation time, and then what follows is only noise. This means that the integral from that point on becomes fairly useless, because it's just a random walk, just an integral of the random noise. So you need to pick a correlation time value where to cut the integral to get reasonable results. This choice is always subjective. There's no real way to pick it objectively correctly, but it might help to compare the integrals calculated by the individual components. So if you calculate each of these separately, and then you can perhaps pick the right correlation time. I can show you how I could do it. Let's just open it this way. Oh yeah, and now we can just go to autocorrelation function, pick the pressure tensor, pick element 4, which will be the first off-diagonal element. Let's just integrate the first 10 picoseconds. That's more than enough. We know it's water with the correlation time of about 2 picoseconds, so 10 is more than enough. Let's click generate. Okay, and let me now add the other two components. So component 5. And component 6. Yeah, and now you can see that down here, there's a region where the 3 components are very similar, and then they start diverging all over the place and even going negative. So of course, these final values here are completely useless. What is important is the value here when the components are still fairly similar. So that would here correspond to some, I don't know, maybe 5 picoseconds from the start. And the calculated viscosity in atomic units would be around 2.31. Converting this to SI units means multiplying it by a conversion factor that you can find at the tutorial. So let me just go, oh, no. Let me just go back to my slides. We do have a tutorial on the website for this, which will explain more details. And we are also about to add a new method for calculating viscosity by shearing the system in a non-equilibrium ND manner, which is much more efficient than this. So if you wait till the next release, you will already be able to calculate it in a much more efficient manner. And finally, for the solid state people among you, I have added a slide about mechanical properties. You can also use AMS to calculate things like Young modulus, the shear moduli, Poisson ratio, all kinds of yield properties by fitting these parameters to the measured stress tensor when you apply some external strain using the MD deformations feature. We also have a tutorial for this, which includes some scripts to analyze it. And the next release will also have built-in analysis in AMS Movie, so you wouldn't even have to run a new script if you download the development version. There are fairly many options on the MD deformation panel. It can be fairly daunting. There's a few of them. I will just show you quickly. So if I just open this, for example, in AMS input. No, I don't want to. So MD deformations is here, and if you add a new deformation, you can see there's very many options. You just pick one of them. Typically, one of the most frequently useful is the target length. When you just set the length of each lattice vector that you want to drive it to, and the MD driver will then gradually increase or decrease the length from the current value towards the target. Or you can set this so-called length velocity, which is just a constant increment to the length of each lattice vector that is added every time step. But if you need to deform the lattice in a very complicated manner, so shear it in some way, you can also use the target lattice or the lattice velocity, where instead of setting the length of the vectors, you set the individual lattice components. And if you feel doing something very advanced, you can also use this strain rate matrix, which is something that just multiplies the lattice matrix by a given strain every time step. So that's pretty much an expert feature that is rarely useful. You can also, apart from a single deformation that just goes from the initial state to the target state and stops there, you can also have oscillatory modulations. So you can have a sine wave modulation that will just gradually shrink and expand your box to accumulate more data for the fitting to Young or shear modulus, for example. Yeah, and that's it. So let me summarize what I've talked about. When using thermostats and barostats, take care not to pick a wrong setting and disturb your dynamics. The Barostat methods are very good for equilibrations, less so for productions. So for production, constant pressure simulations, use the NHC and MTK methods. And don't use short time constants unnecessarily. Always make sure that thermostat is only as strong as you need it to keep the temperature in check, but don't just blindly set it to 100 femtoseconds. The restart feature is something you need for exact continuation, but if if you need to change anything, just set the initial velocities or have AMS input do it for you. And always, if you're running an ME simulation, monitor the basic properties to check that your system is properly equilibrated, things aren't drifting in any direction, and everything's converged. AMS Movie can plot most of the time evolution plots for you, but if you feel like using an alternative, you can also access the same data using Python scripting or the ReaxFF compatibility script. And finally, if you want to calculate some more advanced properties like the dynamic properties of liquids or mechanical properties of solids, check out the tutorials on our website. At this point, I would like to thank you for your attention, and I'm glad to answer any questions.
Yeah, absolutely beautiful. Thank you very much for this. Yeah, so maybe I can kick off with one question that came up and also combine that with the question from the audience. So regarding the shortest time step or picking a time step for the thermostat and for the integration itself, what would I do if, let's say, I have a system and in the beginning they are all normal bonds, but then suddenly there is, let's say, a H2 formation or so. And H2 is the strongest chemical single bond, and it's also pretty short in bond length, so I can expect the frequency of that to be rather high. Should I adjust this then, or should I take this into account? Or?
Yeah, it depends. Like as I've shown, there's quite a bit of buffer region between what is needed for great accuracy and what is still stable. So if there's just a few hydrogen molecules in a system, the rest of their surroundings will just thermostat them away, and your system will not blow up. The motion of these hydrogens will be a little less accurate if you use a 1 femtosecond time step, but the system will not explode. So if you're not entirely interested in just H2 vibrations, maybe you can live with a 1 femtosecond time step. But if you are interested in the fine scale dynamics of this particular molecule, you will probably have to go to 0.5 or so. That is, yeah, something to be checked and tested.
Yeah, so then there is the question about a time step of 4 femtosecond. Would that be too much for a boron carbide system? So also something very hard.
I must admit, I have no idea what the vibrations in boron carbide look like, but I would suspect that 4 femtoseconds is going to be a little bit on the high end, maybe even past the limit of reasonable accuracy. Because yeah, a diamond can pretty much survive 2 femtoseconds correctly, but you can't go much further. I suspect boron carbide will be fairly close to diamond in behavior, but I don't really have personal experience with this.
Mm-hmm. And this also then, does this matter if this is a different type of ensemble, or does that vary between ensembles?
Yeah, well, if you use a thermostat like Berenson, you can mask inaccuracy by just draining the excess energy or putting energy in, and that can compensate for quite a lot of inaccuracy in the integration. But then, yeah, the quality of your results is still definitely affected. Maybe you do not care. Maybe you are only looking for plus minus 20% estimates of some properties. So this accuracy will be okay for you. But I would recommend always checking energy conservation and stability in NVE if you suspect your time step might be a little bit too high. And then, yeah, you'll see whether things are going well.
Yeah. So then, okay, the next question is a bit more technical. When are the recordings usually available? Any links for them? Yeah, so there is no usual yet because we just started and it's all pretty new. So we had a little bit of trouble in adding captions to the last recording, but now we have figured it out. So I hope to be able to send that out later today or tomorrow at the latest. And from there on, yeah, we have some helper students, hopefully, who help us accelerate to add these captions, and then we should be able to send that out, hopefully a bit faster. Yeah, so another question which came up was, so you're talking about equilibrium. What is a good way of determining whether your system is in equilibrium? Apart from following the procedure you detailed in your slides, when do I see whether my system is equilibrated or not?
Well, there's no guaranteed way to get a stamp certifying your system is in equilibrium. But you can check easily if your system is not in equilibrium. There will be a drift in typically the potential or total energy if you just run the system for a while. Because if you generate a random set of water molecules and you just compress it into a box, there will be hundreds of picoseconds passing before the fine structure of water arranges, and you will see the potential energy gradually going down. So your system will have the right density from the start, it will have the right temperature from the start, but the structure will still be evolving, so you will see the potential energy slowly going down. So that's the kind of things to look for. If you see no drift in any of the important quantities, you can assume you're already where you want it to be, but there's no way to certify that.
Then another question is, which parameters for a thermostat would you recommend for the problem of CO adsorption on a palladium nanoparticle?
Yeah, that's hard to give a guaranteed good value off the top of my head, but given that there's no light atoms involved, and probably not a lot of energy liberated during the adsorption, I would start from some relatively conservative values, like, I don't know, 1 picoseconds time constant, and then see if that keeps the temperature in check. If you have a huge jump in temperature once the molecule adsorbs, then you need a more aggressive thermostat. But apart from that, you should be fine.
And given that this kind of adsorption problems or like surface chemistry in general, would that be also a case where you would need to apply 2 different thermostat regions or 2 different thermostats at that?
You can try that. That would be a guaranteed way to always keep the energy in check, but you might be getting a little far from the actual physics, because if you have a real molecule coming close to the surface, there will be some energy liberated by the adsorption, and the molecule will heat up for a while if this happens in the real life. So if you enforce an extra thermostat on just these 2 atoms, you will of course drain that energy away, but it might be fairly far from what would be happening in real life. So you can always simulate anything, but sometimes you might be getting far from the truth.
Right. Then Theo asks, when using reactive force fields or even ab initio MD, should you take care of any special points compared to non-reactive force field MDs? Let's say about large reaction heats or so. I could imagine probably the potential being noisy being another point.
Yeah, that is pretty much it. So you will typically need a shorter time step than what you can afford with non-reactive force fields and well-behaved systems. So for ReaxFF, half a femtosecond is pretty much already the limit. So going to 1 femtosecond with ReaxFF might be a little too aggressive. Sometimes you need to go all the way down to a 1/4 femtosecond for ReaxFF to keep your simulation stable if it is releasing a whole lot of energy. Apart from using typically a factor of 2 shorter time step and sometimes a more aggressive thermostat to drain away the excess heat from the noisy potential, everything else should still work the way it works for non-reactive force fields.
Mm-hmm.
If I may add to that, there are also situations where I found where it matters that your starting structure is very same. Like for example, this when you polymerize something, there's this fixed bond create where you just magically let bonds appear, and that works if you can never dissociate, but that won't work with ReaxFF. Yeah,
that is actually a great point. So reactive force fields by their nature, or even ab initio methods, react in a much more violent manner to any local concentration of heat. So yeah, molecules will start tearing apart and flying all over the place, even though a normal non-reactive force field could survive a water molecule overheated to 1,000,000 kelvins, because yeah, it would just stretch all the way to a kilometer apart and then come back again. But yeah, that is something that a reactive force field won't survive. So often you need to be more careful with your preparation to avoid liberating a whole lot of energy in any point.
Then there is a question about properly defining a pH value in water boxes for molecular dynamics, and if you would have any advice on that, and if you think whether there is a box effect regarding that.
Yeah, well, this is an entire scientific field in itself. Unfortunately, we don't have any constant pH methods in AMS yet. So running an MD simulation at a particular pH will be hard in general, unless you are talking about very extremes of acidity or basicity, where you can just have one excess proton in there. Because otherwise, if you just calculate the concentration of protons you would need in your system to get a pH of 6, you would have to have a super huge box to be able to have at least one proton in there. So the normal solution for this is Monte Carlo methods that will just gradually add or remove protons in parts of the system to keep the average amount of protons to a particular value, so that the average pH would be correct. But we don't have any of those methods yet, so you would probably have to look elsewhere if you need to run at a particular pH. But if you need a very acidic solution where you can just throw a few protons in or a few OH minus ions, then that is something you can do in AMS.
Yeah, and this is a general phenomenon of modeling. So usually what you're able to treat is typically far away from any kind of lab environment, be it pressure or be it ionic concentrations and pH values at that. So that's a bit of a general problem. But then, so the solution for this would look in principle like a variant of grand canonical Monte Carlo, or?
Yeah, you need a grand canonical ensemble with the chemical potential of the protons, which corresponds to the pH. So that is something we don't have at the moment.
Yeah. Then there is another question by Dong Ming. UFF is fairly enough for classical molecular dynamics simulation, but can force fields like amber or modified GAFF used to build new molecules? Also depends a bit on what you mean by building new molecules. Maybe if you could elaborate on that, Dongming. But in the meantime, can you comment on amber and modified GAFF?
Yeah, so we do have, or the force field engine does support amber force fields. It does support the amber force field input format. So if you get any kind of external force field into the same text format that Amber expects, you can load it with the force field engine and use it there. So that you can do. You will typically have to assign the atom types manually if using an external force field. So you will have to open the atom details panel in AMS input and then set the atom types by hand. Or import them from elsewhere. You can copy paste the entire column from somewhere, and then the GUI will fill it in. Regarding UFF, depends on your definition of fairly enough. One thing to keep in mind is that the classic UFF does not have any charges on anything else than water molecules. So electrostatics are completely neglected unless you supply your own set of charges. That's something we've already been doing for some applications where you just calculate something like CM5 charges on your molecules and then you assign them to the atoms. But apart from that, yeah, UFF is a general potential that focuses on being general and not on being accurate for any particular set of molecules. Right. So it will give you the right kind of ballpark behavior for organic molecules, but it will typically be very far in quality from the dedicated force fields like amber for biomolecules, for example.
Do you have any idea? So the example then brought forward is PF6 anion as a molecule. That sounds rather extreme. How well would Amber or modified GFF do for such things?
Not sure if there are parameters for that, but there will definitely be Amber-like force fields for PF6 minus. So you probably need to just find the parameters for that and possibly convert them into the right format to be able to load them. I wouldn't have high hopes of having ready-made parameters in the force field we ship. That is probably quite unlikely. You will have to supply some kind of parameters on your own. But if you don't care about the internal dynamics of your PF6 minus, maybe running UFF with some extra QM-based charges on top is already enough. If you just need a charged atom in your a charged molecule in your solution and don't really care about the internal vibration about that molecule, might already work. We also do have constraints, so you can also just freeze the bonds at the particular lengths if you know, they should be about this size, and then you don't need the parameters for them at all, and maybe that might already be enough for your purposes. I don't know what.
Yeah, so then another technical question regarding hands-out for the first course. So that was, of course, an invited speaker. We do not really have his slides available. However, I hope the recording can solve that once we put it up, which, as said before, should be either happening today or tomorrow. The next question is then, would you be able to obtain quantities like surface tension or interface tensions as properties?
Yeah, but not directly out of the box, but you should be able to calculate things like the surface tension from the pressure tensor that you get from the MD driver. So if you, for example, have an interface or a membrane or something in the XY plane, then looking at the XX and YY pressure tensor components you should be able to convert that into surface tension values. Or you can even study stretching and squeezing the box in that direction, and again calculate mechanical properties, so like stiffnesses, stuff like that. But I don't think you can get that out of the box from AMS movie. You will probably have to resort to some kind of Python scripting or any other custom way to analyze the data. So the data should be there, but we probably don't have a ready-made tool for that.
Yeah. Sticking to interfaces, what should you take care of when you deal with a system that has a solid moiety and liquid part? So how should you handle the interface regarding thermostat and barostat?
Yeah, so for thermostat, this is often, or depending on the potential, but often the case of what I mentioned before, a heterogeneous system where the different parts will be heated up by integration or force errors at a different rate. So you might have to use a separate thermostat for the solid and a separate thermostat for the liquid to be able to have something that does not have a net flux of heat between the two parts. And regarding barostats, there shouldn't be much of an issue. You will almost certainly need to use the barostat in the anisotropic mode where the different axes of the cell are scaled independently, but that is the default mode, so you shouldn't have to care much about that. Apart from that, solid liquid interfaces aren't very hard to model. So this should be safe.
Okay, so I take it that would then be that you actually use a 2D periodic model for modeling the surface and not some kind of repeated slab model, is it?
Well, that depends on the application. I think for the most common solid liquid interfaces, you would actually want a 3D system where you then get two interfaces for the cost of one. But yeah, that might depend on the application. But in some cases, 3D boxes are still more efficient or better than 2D or 1D boxes, because some of our methods can still only work with 3D systems. For example, the force field engine will only do about long-range electrostatics if you use a 3D box. So if you need accurate electrostatics with a non-reactive force field, you will want a 3D box in some way. So probably just a tall box with the liquid inside and a slab of the solid.
So which thermostat would be best to handle a system with ReXFF MD?
Yeah, that is pretty much the same thing with thermostats in general. If your simulation is already equilibrated and stable enough, you can probably run with NHC with a reasonable time scale. The time scales will typically be shorter than it's in, say, non-reactive simulations, because there will be much more energy being liberated by the ReXFF potential and also by any reactions. So yeah, typically you can still use Barostat for equilibration and NHC for production runs. But sometimes if you have a very violent local reaction and you need to avoid overheating the surroundings of that part, there is also a special mode of the Barostat thermostat by setting this local option in AMS input, which will then thermostat every atom separately instead of the system as a one big whole. So that is a way to equilibrate systems where there's some local energy concentration, which will and drain away in this way. It's not very good for productions, but yeah, it will destroy any kinds of fluctuations even on the interatomic scale. But if you just need to equilibrate a reactive force field without it burning up, this is typically the way that can help you.
So if there is a gas reacting with a metallic surface and you try to model that with ReXFF molecular dynamics again, what is better then? Would you increase the pressure rather by increasing the number of gas molecules, or would you compress the system orthogonal to the surface, basically?
Yeah, that depends on where you're starting from and about how much you need to increase. So I would say probably you will need a combination of the two. You will probably want to end up with a system that is still significantly full of gas, so not a few molecules squeezed between two slabs or anything. Yeah, one thing I forgot to mention in the presentation is that as of now, our barostats only work for 3D systems. You won't be able to barostat a 2D system. That's something we want to fix, but not had time to do that yet. So you will need a 3D system, and you don't want your solid metallic surfaces to come close to each other and just end up sandwiching a few molecules. So yeah, there will be some compression, but if that's not enough, you will need to add molecules. ReXFF uses a fixed 10 angstrom cutoff, so anything that's further than 10 angstroms is simply ignored for the purposes of non-bodied interactions. So yeah, as long as your gas part of your box is at least 10 angstroms thick, it does not see more. Oh, no, 20. Yeah, you have to have the whole sphere in there. Yeah, so you need at least 20 angstroms thick gas not to see two interfaces at once. But apart from that, yeah, you will just start from some number and then compress. If you have some particular target pressure, you will probably want to use a barostat to enforce that pressure. So some compression will be happening just by virtue of using a barostat.
Right. Yeah. So when you model surface adsorbed nanoparticles, where there is propane or propene adsorbed with ReXFF, does it make sense to use different temperatures for the solids as well as for the molecules?
Yeah, that is something that comes close to one of the previous topics we discussed, where you adsorb this molecule on the surface. I would say if you know the real physics work that way, maybe you want to actually do that. But in real life, there will be some heat transfer, and the temperatures will probably equalize at some point, or I don't know what the actual process, whether there's a reaction happening there, and what the time scale of that is. So how much thermalization will occur in the real life. So I would
basically, if you add a different temp, or if you change the temperature in one part, you need to be sure that there is a good reason for it, right? That's something.
Yeah. Because if you add two thermostat, you will be enforcing some heat flux, some temperature gradient, and if that temperature gradient does not exist in reality, you're simulating something artificial. So I don't know. Yeah. I'm not familiar with this system or with what exactly you want to model, but I would say maybe you don't need two thermostats for this because you might be forcing it into something that's not happening in the real world.
Yeah. So I came across recently about this on a similar example, but there you have, like, you try to mimic the thermal properties of the bulk underneath the surface, and you place the thermostat there. And on top you have some high energy particles hitting the surface, and that heats it up, of course, but that happens naturally. But yeah, at least in my case, enforcing this in any way doesn't seem like a good idea. So to wrap this one up. Yeah, so as far as I can see, those were all the questions. Ole, do you have some final comments?
I enjoyed it very much, Tomáš. Thank you very much. It was lovely. And other than that, I think I'm happy.
Great. Yeah, in the hope that everyone else is happy too. I hope to see you again on the next session, which is this Thursday, same time as always. And yeah, so clarifying all the technical issues, we should be able to upload the recording rather soon. The slides can be downloaded here, at least for this session, hopefully for the next ones too. Besides that, yeah, I would like to wish you a pleasant rest of the day wherever you are. And yeah, hopefully you can tune in again the next time. Goodbye.
Yeah, thanks everyone for watching. Goodbye.